Since we already know that how the sampling distribution of the sample proportion is constructed, and it has a mean, mu, p cap, and its standard error, sigma, p cap. We use this information we mathematically obtain in the previous module to observe it using a real-life example. From the 1999 to 2000 National Health and Nutritional Examination Survey, which is known as NHANES, show that 31% of the US adults ages 20 to 74 are obese. We designate this population proportion as P equals to 0.31. Now the problem is that if we want to validate this information, we randomly select 150 individuals from this population. And we want to know that what is the probability that the proportion in the sample who are obese will be as great as 0.40. So there are a few observations we can make from the statement given above, that the sample size is 150 with P equals to 0.31. Since both NP and N1 minus P are greater than 5, that is 46.5 and 103.5. So we can say that this is a case where p cap is approximately normally distributed with mean mu p cap, which is equals to p equals to 0.31, and variance of the sampling distribution of the sample proportion, sigma p square, equals to p into 1 minus p over n, where p equals to 0.31 and 1 minus p is actually q, which is 0.69, whole thing divided by 150, and the result outcome is 0.001426. Since we know that the p cap is approximately normally distributed, we can simply translate the distribution of p cap into the standard normal. That is z equals to p cap minus p over p into 1 minus p over n. The output is 2.38. And hence, we find that the area to the right of z is 2.38 is 1 minus 0.9913, which is equals to 0.0087, which is the required probability that the proportion in the sample who are obese will be as great as 0.40. Now, since we are translating from a binomial distribution, which is a discrete probability distribution, to the normal probability distribution, which is a continuous probability distribution, we use continuity correction. This continuity correction makes an adjustment for the fact that the discrete distribution is being approximated by a continuous distribution. So suppose we let x is equals to np cap. To apply the continuity correction, we compute zc equals to x plus 0.5 over n minus p divided by under root pq over n when x is less than np. And we will use the continuity correction and calculate the z out of it by zc equals to x minus 0.5 divided by n minus p divided by pq over n under root when x is greater than np. So this is the rule we often use when we are applying the continuity correction and when we are translating from the binomial distribution to the normal probability distribution. And using this continuity correction in the above example where we are studying the obesity, NP turned out to be 150 multiplied by 0.4, which is equals to 60. And then ZC equals to 60 minus 0.5 divided by 150 minus 0.31, which is the population proportion, divided by 0.31 into 0.69 over 150 square root, which is the standard error of the sampling distribution of p cap, equals 2.30. And hence, finding out the probability that p cap is greater than or equals to 0.40 will be equals to 1 minus 0.9893, which is equals to 0.0107. And this value is slightly different from the value we obtained first because of this continuity correction. And most of the time, when we say that binomial distribution is approximated by the normal probability distribution, we prefer using the results obtained after applying the continuity correction. But if the sample size is too large, that's where the results with the continuity correction and without continuity correction may be the equal. Let's take another example where researchers have studied the use of prenatal care among low-income African American women. She found that only 51% of the women had adequate prenatal care. Hence, the P equals to 0.51. So let us assume that for the population of similar low-income African women, 51% had adequate prenatal care. If 200 women from this population are drawn at random, so sample size is 200, with the probability that less than 45% will have received adequate prenatal care. So we are interested in knowing the probability that P cap is less than equals to 0.45, and using all the information where mu P cap is equals to 0.51 and sigma P cap equals to 0.00125, we compute Z because we are assuming that it is approximately normally distributed. Hence, the Z turned out to be minus 1.70. Hence, the area to the left of minus 1.70 using the standard normal curve is 0.0446. Therefore, probability P cap is less than equals to 0.45 equals to probability Z less than equals to minus 1.70, which is equivalent in the P cap is less than equals to 0.45. Hence, the answer is 0.0446. There are a number of ways one can use the information coming from the sampling distribution and draw inferences about the population based on the sample.